Picture this. You're standing at the bottom of a mine shaft in Virginia City, Nevada. The year is 1878. You're 2,000 feet below the surface, deeper than any building in America is tall. The air is hot, over 120 degrees, and so thick with moisture it feels like breathing underwater. Your candle throws shadows against the rock walls, and somewhere in the darkness ahead of you, you hear it. A sound like distant thunder. But it's not coming from above, it's coming from below. Water. Millions of gallons of it, pressing against the rock from every direction, seeping through 1,000 invisible cracks, pooling in the tunnels you carved out yesterday. The Comstock Lode sits in one of the most geologically unstable regions in North America. The rock is fractured, the aquifers are vast, and every single day, the mines of Virginia City take on water faster than some rivers flow. Without something to push that water back up to the surface, you would drown. Everyone down here would drown. The richest silver deposit in American history would fill up like a bathtub, and $500 million in ore would be lost forever, beneath a lake that had no business existing. But you're still standing here, still breathing, still working. Because somewhere above your head, a machine the size of a small building is running. It runs every hour of every day. It has been running for years. It will continue running for decades. One machine, fighting 10,000 gallons of water every single minute, holding back the floods so that men like you can work. This is the story of the pumps that made America's deepest mines possible, and the men who kept them running at all costs. Let's start with what miners were actually facing when they tried to dig deep into the earth. Water is everywhere underground. This isn't a surprise to anyone who has ever dug a well, but the scale of it catches most people off guard. The earth below our feet is not solid rock. It's a sponge. Every crack, every gap, every porous layer of stone holds water. And when you carve a tunnel through that rock, you're not just removing stone, you're creating a channel for all that water to flow into. In shallow mines, this was manageable. A few buckets, a few men, and you could keep ahead of the seepage. But shallow mines didn't have the richest ore. The valuable deposits, the thick veins of silver and copper and gold that could make a man wealthy, those were almost always deeper, always beyond the water table, always surrounded by aquifers that had been accumulating moisture for thousands of years. The physics worked against you in ways that weren't obvious until you started digging. Water pressure increases with depth. At the surface, an aquifer might seep a few gallons per hour. At 300 feet, that same aquifer could push water through rock fractures at hundreds of gallons per hour. At 1,000 feet, you weren't dealing with seepage anymore. You were dealing with underground rivers that had been waiting for millennia for someone to give them somewhere to flow. And the deeper you went, the more aquifers you encountered. A shaft that passed through 200 feet of dry granite might hit a water-bearing layer at 250 feet, then another at 400, then another at 600. Each layer added to your problem. Each layer increased the total flow you had to fight. Some mines found that their water intake doubled every time they went down another 100 feet. The tin miners of Cornwall, England, understood this problem better than anyone on Earth. They had been digging into the granite peninsula of southwest England since before the Romans arrived. And for centuries, they fought water with nothing but muscle and determination. The bucket chain was their primary weapon. Teams of men would stand in the shafts, spaced along the vertical passage, passing wooden buckets filled with water, hand over hand, up and up and up, until the water reached the surface and could be dumped into a stream. It was brutal work. Your arms never stopped moving. Your hands cracked and bled from the constant wet. The skin on your palms grew thick with calluses, then split open anyway from the relentless friction of wooden bucket handles. And if you ever fell behind, even for an hour, the water would rise past your ankles, past your knees, and eventually past your head. A man named Jenkin Williams worked a bucket chain at the Wheel-Busy mine in Cornwall in 1743. The mine records show that he passed buckets for 11 hours a day, 6 days a week, for 7 years straight. When he finally stopped, it was because his right shoulder had frozen into a permanent hunch from the repetitive motion. He couldn't lift his arm above his chest. He was 34 years old. But bucket chains worked, more or less, for mines that went down a few hundred feet. The problem was that the ore you wanted was rarely found at those depths. By the early 1700s, Cornish mines were pushing past 600 feet. At those depths, a bucket chain required hundreds of men working in continuous shifts, passing water up through multiple relay stations around the clock. The mine at Wheal Vor employed over 200 bucket men at its peak. The noise alone was deafening. Hundreds of wooden buckets clattering against stone walls, hundreds of men grunting with effort, hundreds of gallons of water sloshing and splashing in an endless vertical river. And even with all that labor, the mines sometimes lost the fight. In 1765, Wheal Vor flooded completely. 800 feet of tunnels, years of excavation work, thousands of pounds sterling in investment, all of it underwater within a week. The pumps they had couldn't keep up with a particularly wet spring. The mine owners tried everything. They brought in extra workers, they offered double wages to keep the bucket chains running 24 hours a day. They even tried digging a drainage adit, a horizontal tunnel that would let water flow out naturally by gravity. It took too long. Before the adit could be completed, the lower levels were submerged. The ore was still there, mind you. Perfectly good tin ore, sitting in veins that the miners had been following just days before. But it was unreachable now. The water had won. Some mine operators tried using horses. They rigged up windlasses, giant wooden drums with ropes coiled around them, and hitched teams of horses to walk in circles and pull the buckets up mechanically. It was faster than human muscle alone. A good horse team could lift 1,000 gallons an hour. That sounds impressive until you realize that a deep mine might take on 1,500 gallons an hour during wet season. The horses couldn't keep up. And horses had problems of their own. They got tired. They got sick. They stumbled on the circular paths they walked and broke their legs. Replacing a draft horse cost money that cut into already thin profit margins. A mine owner named Thomas Bolton calculated in 1756 that he spent more on horse feed, horse medicine, and horse replacement than he earned from the tin his mine produced. He closed the operation 6 months later. What the mining industry needed was a machine that could pump continuously, forcefully, and reliably. A machine that didn't get tired. A machine that didn't need to rest. A machine that could fight the water hour after hour, day after day, year after year. And in 1712, that machine finally arrived. His name was Thomas Newcomen, and he was an ironmonger from Dartmouth, England. He had been tinkering with steam power for over a decade, trying to find a practical application for the principles that other inventors had discovered. And his target was always the mines. Newcomen knew that whoever could solve the pumping problem would have a product that every mine owner in England would pay for. The engine he built was a monster. It stood over 2 stories tall. It required a brick engine house to contain it, with walls thick enough to absorb the constant vibration. It burned coal at a rate that would bankrupt a small town. And it was terribly inefficient, converting barely 1% of the fuel's energy into actual work. But it worked. The principle was elegant in its simplicity. Steam would fill a cylinder, then cold water would spray into the cylinder to condense the steam, creating a vacuum. Atmospheric pressure would push a piston down into that vacuum with tremendous force. That piston was connected to a giant wooden beam, sometimes 50 feet long, balanced on a central pivot like a seesaw. When the piston went down, the other end of the beam went up, and attached to that rising end was a chain connected to pump rods that reached hundreds of feet down into the mine. Up and down, up and down. 12 strokes per minute. Each stroke lifted dozens of gallons of water. And unlike horses, unlike men, the Newcomen engine never needed to sleep. The first Newcomen engine was installed at a coal mine in Staffordshire. Within a year, orders were pouring in from across England. Within a decade, the engines were being exported to Europe. Within 50 years, hundreds of Newcomen engines were working in mines from Scotland to Spain. Mines that had been abandoned to flooding reopened. Shafts that had stopped at 300 feet now pushed down to 600. The tin and copper of Cornwall flowed to the surface again. A mineral famine that had been threatening European industry was averted. And it was all because of one machine, pumping water in the darkness, day after day after day. But the Newcomen engine had a serious limitation. It was incredibly fuel-hungry. The constant cycle of heating steam and then cooling it with cold water wasted enormous amounts of energy. Mines located near coal fields could afford to run these engines because fuel was cheap. Mines in remote areas could not. The cost of hauling coal to feed the engines sometimes exceeded the value of the ore they allowed you to extract. This is where James Watt enters the story. In 1769, Watt patented his improved steam engine with a separate condenser. Instead of spraying cold water into the main cylinder, Watt diverted the steam to a separate chamber for cooling. This meant the main cylinder stayed hot, which meant far less fuel was needed to generate each new batch of steam. Watt's engine used perhaps a quarter of the coal that a Newcomen engine required for the same work. This changed everything. Suddenly, steam pumping was economical in places where it had been impossible before. Mines in the mountains, mines on islands, mines far from any coal deposit could now run pumping engines by importing fuel. The geographic constraints that had limited deep mining began to fall away. And when Watt's patents expired in 1800, a new generation of engineers took his ideas and pushed them further. Richard Trevithick in Cornwall built high-pressure engines that were smaller, lighter, and more forceful. Arthur Wolff developed compound engines that extracted more work from each pound of steam. And a school of engineers emerged in Cornwall who dedicated themselves to building the most efficient pumping engines the world had ever seen. They called them Cornish beam engines, and they were magnificent. A fully developed Cornish beam engine was not just a machine, it was architecture. The engine houses built to contain them were constructed from granite and brick, sometimes standing 100 feet tall, with walls 3 feet thick to absorb the vibration of the working beam. The rocking beams at their hearts were made from cast iron, weighing 15 or 20 tons, balanced so perfectly that a child could push them into motion by hand. The pump rods they drove extended down into the earth for 1,000 feet or more, chains of iron connecting the surface world to the flooded depths below. The largest Cornish engines could pump 5,000 gallons per minute from depths of 2,000 feet. Imagine that for a moment. 5,000 gallons is roughly 19 tons of water, lifted 400 times the height of a grown man, in 60 seconds. That's what these machines could do. And they did it hour after hour, month after month, decade after decade. A Cornish engine at the United Mines in Cornwall ran continuously for over 40 years. When it was finally dismantled in 1895, workers found that the beam had worn grooves into its pivot bearings several inches deep. The iron itself had been shaped by decades of motion. The engine had become a geological feature, as much a part of the landscape as the granite cliffs around it. By 1850, Cornwall had the most advanced mine pumping technology on Earth. And when America started digging its own deep mines, it was to Cornwall that they turned for help. The Comstock Lode changed everything. In 1859, prospectors in the mountains of western Nevada found something extraordinary. What they thought was troublesome blue mud clogging their gold sluices turned out to be silver ore of unbelievable richness. Assays came back showing values of $3,000 per ton, more than 10 times the value of typical gold ore. Word spread across the country. Within months, thousands of men poured into the region. Virginia City rose from the desert like a fever dream, eventually becoming one of the largest cities west of the Mississippi. But the Comstock had a problem that made all of Cornwall's flooding look trivial. The ore bodies of the Comstock were not neat, predictable veins. They were massive, irregular deposits buried beneath layers of crumbling clay and fractured volcanic rock. And that fractured rock was saturated with water. Hot water, heated by geothermal activity to temperatures that could scald flesh. Mines that pushed below a few hundred feet hit water that was over 150 degrees Fahrenheit. It gushed from every crack. It pooled in every tunnel. It filled the air with steam that burned your lungs. And it kept coming, relentlessly, endlessly, as if the mountain itself was trying to drown the men who dared to take its silver. The early mines tried the old methods: bucket chains, horse whims, small steam pumps purchased from San Francisco. Nothing was enough. One mine, the Ophir, flooded so completely in 1861 that the owners simply gave up and walked away. The equipment was abandoned underground. The shaft was sealed. Thousands of dollars in investment was written off as a total loss. Another mine, the Savage, saw its pumps overwhelmed during a particularly wet season in 1863. Water rose faster than the small steam engines could remove it. The superintendent, a man named John Church, ordered an emergency evacuation at 2 a.m. Miners scrambled up ladders in the darkness, their candles guttering, water splashing at their heels. The last man out reported that water was rising at nearly a foot per minute. If the evacuation had started 30 minutes later, men would have drowned. The mining companies realized they needed something far more substantial. They needed Cornish expertise. In 1863, the Gould and Curry Mining Company began construction on what would become one of the largest pumping installations in American history. They recruited engineers from Cornwall, men who had spent their lives working beam engines and understood the art of large-scale pumping. They imported castings from foundries in San Francisco that had learned Cornish methods from English blueprints. They built an engine house of brick and timber on the slopes above Virginia City, and inside it, they assembled a beam engine with a cylinder 60 inches in diameter. This engine could pump 4,000 gallons per minute from the deepest workings of the mine. Its beam weighed over 20 tons. Its pump rods extended down through a vertical shaft for nearly 1,000 feet. And when it ran, when the beam rocked on its pivot and the pump rods plunged into the earth, you could feel the ground shake for a quarter mile in every direction. But one pump was not enough. The Comstock was too wet, too deep, too fractured with aquifers. By 1870, there were over a dozen major pumping engines operating along the Lode. The Consolidated Virginia had 2. The California mine had 3. The Yellow Jacket, the Crown Point, the Belcher, each had their own dedicated pumping installations. Together, they lifted something like 20 million gallons of water every single day. 20 million gallons. Try to picture that. Imagine a river flowing up out of the earth. A river created entirely by machines. A river that had to flow continuously, or thousands of men below would die. Running these pumps required fuel. Massive quantities of fuel. The forests of the Sierra Nevada were stripped bare to feed the boilers. Wood was hauled by wagon from cutting camps 30 miles away. A single large pumping engine could burn through a cord of wood every hour. That's a stack of timber 4 feet wide, 4 feet high, and 8 feet long, converted to ash and smoke and steam every 60 minutes. The Comstock's pumps burned through entire forests in a single season. Later, when the nearby forests were exhausted, the companies built a flume, a wooden channel that snaked through the mountains for 15 miles, floating cordwood down from more distant slopes. The V-flume of the Sierra Nevada became famous in its own right, an engineering marvel built solely to keep the pumping engines fed. Lumberjacks worked year-round in the High Sierra, cutting timber that would never become houses or furniture or railroad ties. It would all go into the fireboxes of the pumping engines, sacrificed to keep the water at bay. The scale of consumption was almost industrial in its own right. At its peak, the Comstock's pumping operations consumed over 500,000 cords of wood per year. That's enough lumber to build a small city. That's enough trees to cover thousands of acres. All of it burned. All of it turned to ash. All of it necessary to keep the water from winning. And the engines ran, day and night, summer and winter, Christmas and Easter. They never stopped. They could never stop. A man named Patrick Flanagan worked as a pump engineer at the Consolidated Virginia for 11 years. His job was to monitor the great beam engine that kept the lower levels dry. He worked 12-hour shifts, 6 days a week. When he arrived each morning, he walked around the engine, checking every bearing, every valve, every joint. He felt the pump rods for vibration. He listened to the rhythm of the beam. He learned to read the machine's moods the way a farmer reads the weather. If anything went wrong, if a bearing seized, or a rod broke, or the boiler pressure dropped, Flanagan had minutes to fix it. Not hours, minutes. Because water was always pressing. Water was always waiting. And if the pump stopped, the water would rise at a rate of several feet per hour. Men working at the bottom of the mine would have to evacuate immediately. Timbering would be crushed. Tracks would be warped. Equipment worth thousands of dollars would be destroyed. Flanagan saw it happen once. In February of 1872, a valve failed on the main pump during a night shift. By the time the repair crew arrived, water had risen 80 feet in the lower workings. 3 men who had been mucking ore at the bottom level barely escaped with their lives. They came up the ladder with water lapping at their boots, climbing as fast as their exhausted legs could carry them, knowing that the flood was climbing right behind. It took 3 weeks to pump the water back out and repair the damage. 3 weeks of production lost. 3 weeks of wages for 1,500 workers who had nothing to do but wait. After that, the company installed backup pumps. But backup pumps required backup engines, backup boilers, backup fuel supplies. The costs multiplied. At its peak, the Comstock Lode spent over $1 million per year just on pumping. That was more than the entire annual budget of some state governments. It was one of the largest single operating expenses in American industrial history. But the silver kept flowing. Between 1860 and 1880, the Comstock produced over $300 million in ore. Adjusted for inflation, that's somewhere between $7 and $10 billion today. None of it would have been possible without the pumps. And the Comstock was not alone. In Michigan's Upper Peninsula, the copper mines faced their own battles with water. The Calumet and Hecla Mining Company, which would become the most profitable copper mine in the world, installed Cornish pumps that reached down nearly a mile into the earth. The rock there was harder than Nevada's crumbling volcanic stone, but the aquifers were just as relentless. Water at Calumet ran cold instead of hot, 40 degrees instead of 150, but it ran in quantities that tested even the largest engines. The Quincy mine, a few miles from Calumet, operated what was for many years the world's largest steam hoist. But alongside that hoist sat pumping engines that worked just as hard. A mine superintendent named William Harris wrote in his 1879 annual report that pumping costs accounted for nearly 40% of the Quincy's total operating expenses. 4 cents of every dime spent to extract copper went to fighting water, not to digging, not to processing, not to shipping, just to keeping the mine from drowning. In Butte, Montana, the copper mines ran so deep and so wet that they eventually required electric pumps operating around the clock at multiple levels. The Anaconda mine, which would become one of the most productive copper operations in history, installed its first pumping system in 1881. By 1900, the pumps at Anaconda were removing over 8,000 gallons per minute from shafts that extended more than 1,000 feet below the surface. The men who tended these pumps were a special breed. They worked in conditions that would be illegal today. The engine houses were deafening, filled with the crash and hiss of steam machinery. The noise wasn't a background hum. It was a physical presence that vibrated in your chest and made normal conversation impossible. Pump operators communicated through hand signals, through lip reading, through written notes passed back and forth. After a few years, most of them had permanent hearing damage. After a decade, many were effectively deaf. The temperatures swung from freezing in winter, when cold air poured through ventilation gaps and frost formed on metal surfaces, to sweltering in summer, when the boilers turned the buildings into ovens. A pump house in July might reach 130 degrees near the firebox. Men working the coal shovels would strip to the waist and still drip sweat onto the floor, creating puddles that hissed when they touched hot iron. Pumpmen breathed air thick with coal smoke and steam. The coal they burned was rarely high quality. It was whatever could be hauled to the site cheapest, which often meant low-grade fuel, full of sulfur and impurities. The smoke burned your eyes. It coated your lungs. Old pump engineers coughed constantly, hacking up black phlegm that told the story of years spent breathing poison. Their clothing was never fully dry. Their boots rotted from constant exposure to moisture. Their skin developed rashes and fungal infections that never quite healed. And yet the job carried prestige. A skilled pump engineer was one of the best paid workers in a mining camp. He was also one of the most essential. When the pump man said he needed new parts, he got new parts. When the pump man said the engine needed to rest for maintenance, the whole mine worked around his schedule. Because everyone knew what happened when the pumps failed. A man named James Tregaskis worked pumps at 6 different mines across 3 states over a career that spanned 40 years. He started as a boy in Cornwall, learning the trade from his father, who had learned it from his father before him. The Tregaskis family had been pumpmen for 3 generations. When the Cornish mines began to decline in the 1870s, James emigrated to America, bringing his knowledge with him. He worked the Comstock. He worked Butte. He finished his career at a copper mine in Arizona, teaching younger men the secrets of keeping a beam engine alive. Tregaskis died in 1903 at the age of 67. His obituary in the Bisbee Daily Review called him one of the finest pump engineers in the territory. It mentioned that he had never lost a mine to flooding in 4 decades of work. It did not mention how many nights he had spent awake beside a faltering engine, nursing it through a crisis. It did not mention the arthritis in his hands from working valve mechanisms in the cold. It did not mention the hearing he had lost to years of mechanical thunder. The pumps saved mines, but they also killed men. On March 4, 1893, a pump house at the Franklin mine in Michigan's copper country caught fire. The cause was never definitively established, but most investigators believed it was a spark from the boiler that ignited coal dust accumulated in a storage area. The fire spread with terrifying speed. Within minutes, the entire engine house was engulfed in flames. 4 men were working inside when the fire started. 2 of them, a fireman named Carl Piatilla and an engineer named Thomas Pascoe, managed to escape through a side door. They suffered severe burns on their hands and faces, but survived. The other 2, an oiler named Matti Heikkinen and a coal shoveler named Eric Lindqvist, did not make it out. Their bodies were found in the wreckage the next day, burned beyond recognition. With the pump house destroyed, the Franklin mine began to flood. Water rose at nearly 2 feet per hour. Within 3 days, the lower levels were completely submerged. It took the company 6 months to rebuild the pump works and another 4 months to dewater the mine. The total loss was estimated at over $200,000. But the greater loss, the 2 men who burned to death doing a job that most people didn't even know existed, barely made the newspapers outside Michigan. There were other deaths, other disasters. In 1880, a boiler explosion at the Challer mine in Virginia City killed 3 men and injured 7 more. The explosion was caused by low water in the boiler, a mistake that should never have happened, but did anyway, because the operator was exhausted from a double shift. In 1886, a pump rod broke at the Tamarack mine in Michigan, and the failing chain whipped through the engine house with enough force to crush a man against the wall. His name was Anders Nilsson. He was 24 years old. He had been in America for less than a year, following his brother to the copper country in search of work. The pumps ran on coal and wood, and eventually electricity. They also ran on human lives. But they did what they were built to do. They held back the water. And because they held back the water, America could take the minerals from its earth. By 1900, the United States was producing more copper than any other nation on earth. It was producing silver enough to flood the world markets and trigger political debates about monetary policy. It was extracting lead and zinc and iron ore from deposits that previous generations had written off as too deep, too wet, too dangerous to work. None of this was inevitable. Every ton of that metal came from a mine that existed only because machines fought water day after day after day. Every copper wire in every electric motor, every silver coin in every pocket, every lead bullet in every cartridge. All of it passed through mines that would have drowned without constant, relentless pumping. The scale of what those pumps enabled is hard to comprehend. The Comstock alone yielded enough silver to pay off a significant portion of the national debt accumulated during the Civil War. The copper from Michigan wired the telegraph lines that connected a continental nation. The iron from Minnesota built the railroads that carried that copper and silver to market. All of it came from deep in the earth. All of it required pumps. The transition to electric pumps came gradually. The first electric mine pump in America was installed at the Anaconda Copper Mine in Montana in 1889. It was crude by later standards, a simple centrifugal pump driven by a wire rope from an electric motor on the surface. But it worked, and it pointed the way forward. Electric pumps had advantages that steam could never match. They could be installed at multiple levels throughout a mine, each pump lifting water to the next level up, instead of requiring one giant engine to do all the work from the surface. They didn't need coal or wood fed to them constantly. They didn't require engine houses the size of cathedrals. They were simpler, more reliable, and eventually more efficient. By 1920, the great Cornish beam engines were becoming obsolete. One by one, they were shut down, dismantled, and sold for scrap. The engine houses that had dominated mining landscapes for decades stood empty. Some were demolished. Some were converted to other uses. A few were preserved, more by accident than design, as monuments to an era that was already fading from memory. The Quincy Mine in Michigan kept its steam hoist running until 1931, the last major steam operation in the American copper country. When it finally shut down, workers reported that they could hear the silence for the first time in their lives. For generations, the constant thump of steam machinery had been the heartbeat of the region. Its absence felt like a death in the family. Today, if you visit the mining districts of Nevada or Michigan or Montana, you can still find traces of the pumping age. Ruined engine houses stand on hillsides, their walls crumbling, their roofs collapsed. The great beams were removed long ago, sold as scrap iron during one war or another. But you can see where they sat. You can see the foundations where the cylinders rested. You can imagine, if you try, what it must have been like to stand beside one of these machines while it worked. I tried to find a working Cornish pump engine in America once. A real one, not a reconstruction or a model. They are almost impossible to locate. There are a handful in museums, static displays behind velvet ropes, but none that still run. The knowledge of how to operate them, the instincts that men like Patrick Flanagan and James Tregaskis developed over decades of experience, that knowledge is gone. It exists now only in old technical manuals and the fading memories of a few elderly engineers who saw the last of the steam age. I stood in the ruins of a pump house near Virginia City a few years ago. The engine was gone. The boiler was gone. Even the floor had rotted away, leaving only stone foundations and the vertical opening of the shaft, fenced off now with chain link to keep tourists from falling in. A sign explained that this had been the pumping station for one of the Comstock's major mines. It gave a few statistics about output and depth. It did not mention the men who had worked there. I stayed for a long time. I tried to hear the echoes, the hiss of steam, the crash of the beam, the rush of water coming up from 1,000 feet below. But there was nothing, just wind and the distant sound of traffic from the highway. The pumps are gone now. The mines they protected are mostly closed, flooded again, returned to the water that was always trying to claim them. The aquifers have refilled. The tunnels are dark and silent and full. Whatever ore remains down there will probably never be recovered. But for 60 or 70 years, those pumps won the fight. They held back millions of gallons. They kept thousands of men alive. They made possible the extraction of wealth that built cities and funded governments and changed the shape of the American economy. We don't think about them anymore. We drive through Nevada on highways built with tax money from Comstock silver, and we don't think about the pumps. We use copper wire manufactured from Michigan ore, and we don't think about the pumps. We take for granted that minerals come from the ground, as if that were simple, as if it were easy, as if men didn't spend their lives fighting water in the darkness to make it happen. There was a pump engineer named William Hennessy who worked the Calumet for 31 years. When he retired in 1912, the company gave him a gold watch. The inscription read, "For 3 decades of faithful service." It did not say what that service was. It did not say that Hennessy had kept the water at bay for 31 years, that he had woken from sleep 100 times to the sound of a messenger pounding on his door, telling him something had gone wrong with the pumps, that he had crawled through flooded tunnels to repair broken valves, that he had burned his hands on steam pipes and frozen his fingers on iron in January, and done whatever was necessary to keep the machines running. Hennessy died 6 years after he retired. His obituary mentioned that he had been a mining man. It did not mention the pumps. It did not mention that his work had helped bring 400 million pounds of copper to the surface. It did not mention that without men like him, the Michigan copper country would have been abandoned decades before it actually was. The last thing I want to tell you is this. Every deep mine in the world still has pumps. Modern pumps, electric pumps, computerized and automated and monitored by sensors that Hennessy and Tregaskis could never have imagined. But the principle is the same. Water is always pressing. Water is always waiting. And if the pumps stop, the mines flood. At the Bingham Canyon copper mine in Utah, pumps currently remove approximately 20,000 gallons of groundwater every minute. That's more than twice what the largest Comstock engines could manage. And it runs constantly, every day of every year, because Bingham Canyon is one of the largest open-pit mines in the world, and its operators cannot afford to let the water win. We still need the pumps. We just don't see them anymore. They're hidden away in equipment rooms and service tunnels, humming and whirring where no one ever visits. The men who tend them are technicians now, working for contractors, checking readouts on screens instead of feeling vibrations in pump rods. The relationship between human and machine has changed, but the urgency remains. Somewhere beneath the Nevada desert, beneath the Michigan forests, beneath the Montana mountains, there are flooded tunnels where miners once worked. The water is patient. It filled those spaces as soon as the pump stopped, and it will keep them filled forever. The ore that remains down there is lost. The shafts are drowned. The darkness is permanent, But for a while, for a few brilliant decades, men and machines fought back. They built engines that could pump 10,000 gallons a minute. They ran them day and night for years on end. They held the water at bay long enough to take what they needed from the earth. And then they moved on. The pumps were silenced, the water returned, and the world forgot that any of it had ever happened. Until now. The next time you see a copper wire, or a silver coin, or anything made from metal that came from a deep American mine, I want you to think about the pumps. Think about the men who built them and the men who ran them. Think about Patrick Flanagan, checking his bearings before dawn. Think about James Tregaskis, teaching young men how to listen to an engine's heart. Think about William Hennessy, 31 years in the dark, fighting water. They won their fight, for as long as they could. And we're still living on the fruits of their victory. That's the story of the pumps that made America's deepest mines possible. Machines and men, together in the darkness, holding back the flood.